started exactly in the middle, the point of turning, or is shifted slightly before? This the pipe is symmetrically about.
Oh, so the pipe pulse is symmetric about it, and actually I'll show you. We studied that carefully. So then I answer your question. So when you apply these pulses here, so it's just a matter of applying these pulses. We find that look, the frequency and sensitivity increases now like 1/t squared. So this blue line is the absolute best you could possibly do. And the data points are our measurement results. And you can see we match the fundamental limit very closely. At short times and at long times, we have things get worse because, again, the T2 of the qubit becomes a problem. So overall, we have a 740-fold improvement of the quantum Fisher information, almost 2 orders magnitude more frequency sensitivity given this T2 of our qubit. So this happens to be the absolute fundamental limit, the best you can possibly do. And this fundamental limit was only discovered this year by Andrew Jordan. So it's pretty surprising that this wasn't known before. But to the best of our knowledge, this sort of thing hasn't been studied.
But this is not connected to this theory of all these CPNG pulses and things.
Okay. So that's a good question. What's the relationship between dynamical decoupling?
I'm guessing. I was just guessing that it might be connected to.
So this is exactly the opposite of dynamical decoupling. So dynamical decoupling, you apply pulses to sort of cancel out the noise, and here we're applying pulses to amplify the noise, amplify the signal. So a standard dynamical decoupling sequence would make you less sensitive to it, so it's just the opposite of that. And it's possible someone thought that, oh look, you could make yourself more sensitive to it, but to our knowledge, no one has.
You're actually doing something different here.
But it has a similar feel, and actually the implementation is very similar too. So it's the opposite. Casey?
So this is the limit for a Hamiltonian whose derivative is linear in time, right? So couldn't you presumably make a Hamiltonian as squared or like cubed in time, then its derivative would be t squared?
Okay.
I was going to ask that.
That's a great question. That's a great idea. Yeah. So maybe you could. Okay. So the other case where this works is there may be a reason why you might not be able to find an example that you could do that. Another case where you can have this kind of enhancement is in a case of a Landau-Zener sweep. So you can apply controls during a Landau-Zener sweep and measure energy differences there more accurately. So this is another paper from Andrew Jordan. There may be lots of cases where you get this sort of amplification in your sensitivity, and it's just a matter of like, hey, let's just think about how we could try to do this, because that's actually kind of exciting, and I think that there hasn't been much time to think about it. So, good question.
Doesn't matter on what kind of quantum system, whether there are more eigenstates involved. I mean, here there's only 2 eigenstates. I mean, this is like, if you had a more complicated system, let's say you had a multi-qubit system with a larger Hilbert space, does that change the scheme?
No, it doesn't. So in that case, you would have more than 2 eigenvalues of the derivative of the Hamiltonian with respect to time. But the best you can do has to do with the maximum, the minimum eigenvalues. And in that case, we just have access to those in this case. OK, so in order to do this, it's easy. You just apply these pulses exactly at where your Hamiltonian hits the bottom and the top. And so the question is, how do you know when to apply these pulses? This is ridiculous. You have this insensitivity, but you have to know the frequency ahead of time in order for it to work. So the question is, how sensitive do you need to be? Or another sense is, how sensitive is this technique? So here I'm showing a plot of the quantum Fisher information as I change the phase between the pulse and the ideal pulse. So do I start is it exactly aligned with the antinodes of the Hamiltonian, is just slightly off, and the frequency difference between the two? Okay, so you can see there's a maximum that occurs right when the frequency difference is 0 and the phase is about 0. But you can see it doesn't fall off too quickly. So if I show cuts through this is sort of how the quantum Fisher information degrades as I mismatch the phase and I mismatch the frequency. And the point that this makes is that, and we can show this mathematically, is that the quantum Fisher information at worst decreases quadratically with a mismatch in your parameters. So it's not too hard to get the parameters exactly lined up to do it, or close enough that you have this enhancement. So the blue regions here show how well you can determine the frequency from a very standard Ramsey measurement with no control. You can get it that close. If you can get it that close, then you're applying this thing, you already have the benefit of this optimal control. And then you can think about trying to find your way to the peak of this mountain in the quantum Fisher information. So in order to do this, it would be an adaptive control. You measure the frequency, you get it to 2 digits or something of accuracy, then you apply this thing, you measure it a little longer, and you get it to 3 digits of accuracy, then a little longer, 4 digits, and so forth. And so you you interrogate longer for the longer things, and you can, it turns out all this adaptive stuff just is a very small correction to the overall time you spend measuring. So it turns out that we're fortunate that it's not too sensitive in that respect. OK, so just as kind of an outlook in this, what this is. So frequency sensitivity, the ultimate sensitivity, it turns out these are all the prefactors. It goes like pi over a times t squared times the phase uncertainty. Okay, we have to measure the phase of the qubit. And the way we do it is by measuring, projecting onto the z-axis, or rotating to the z-axis and measuring. And so in that case, our phase uncertainty decreases like 1 over the square root of 4n. It's just a binomial error. But if we had, say, n entangled qubits, and we did this in parallel, you could see that this phase uncertainty would decrease like 1 over n. So that would be the full quantum enhancement in terms of entanglement and in terms of this sort of coherence resource. That's the best you could do. That's something that would be fun for someone who has n simultaneous qubits to do. Okay? So also as an outlook, this benefit only happens for as long as the coherence of the qubit lasts. So if we have some long signal we want to measure the frequency of, what you'd have to do is repeat these measurements, right here with all these pulses, right here with all these pulses, and so forth and so on. And if you're not very smart about it, then you end up sort of just averaging the phase in these separate measurements, like as if they're not correlated. And actually, your improvement's not very good because you spend all this, spend most of your time with this sort of poor scaling. It's a bad way to say that. But if you take into account the fact that these measurements are correlated with one another because they're sampling this overall signal at different phases, you can get a frequency uncertainty that scales like t to the minus 3/2, where now t is not just the coherence of the qubit, but it's the total time of the sampling. So there's an unlimited sensitivity in that case. And so 2 papers just this year came out in Science where they did this with a nitrogen vacancy center. And they see this t to the minus 3/2 scaling. So our technique would give us sort of just a multiplicative improvement on what they have. So it's not, in terms of the total time of the experiment, it's no better than what they do, or it's only slightly better. But this is kind of what we'd expect to do if you just have coherence that lasts for a short time compared to the measurement time.
This is doing something different than what we do.
It's doing something very similar to what we're doing, but maybe is not. It's more optimized to taking something and measuring. It's actually more practical than what we've done because they're actually sampling some signal for seconds or hours or something with something that has a very short coherence time. So they're focusing on sort of how you correlate these things. So it's a kind of a hybrid quantum classical thing. You have a quantum measurement, and then you have you kind of see how they're correlated at other times. So it involves a classical Fourier transform in these quantum measurements. So that's.
Combine those?
So what we did is focused on just this part here, and showed that really you can achieve the absolute optimal sensitivity here, which is something they didn't really think about. They thought about how do we maximize the sensitivity, this one here, which is really the more practical question. But they did that before we did this, which was some of the inspiration for this work. Okay, so that's the story about frequency control. I got some questions along the way. Do you want to ask any questions before I move on to sort of the second half of the talk? And I'm also not sure how much time I have. Oh, it's almost been, I'm almost out of time.
We have like 15 minutes.
Okay, we'll make the second part snappy. So maybe I'll move on and take questions at the end. Is that okay with everybody? Okay. Zeno, so quantum Zeno effect. The name Zeno comes from Zeno's arrow paradox. And his paradox is the following. Zeno says an arrow cannot move. And the reason is the following, or his reasoning is this. Let's divide time into an infinite number of durationless points. Okay? Now, the arrow has 2 options. If it's at location A, it can either stay at location A, or it can go to location B. Now, because it's already at location A, it can't go there. But because no time elapses, it can't go to location B. Therefore, it can't move. So you can do what you, with Zeno's argument what you will. But it's the idea that, I don't know, what is the idea? The idea is that somehow by dividing time into these things or sort of thinking about it in very often, where is it, where is it, where is it, you can alter its dynamics. That's the case. So to understand the Zeno effects in quantum mechanics, it's nice to think about the Schrodinger's cat paradox. Okay, this is this thought experiment where you have a box, and in the box you put a radioactive atom and a little vial of poison, and you set it up so that if the atom decays, this poor cat in the box will be killed. And the idea behind the Zeno effect is if we were to, for example, check on the box, we can see, the cat's still alive. Good. Start over. The cat's still alive. Start over. So each time you check on the cat, you find the cat's alive. This means the atom must not have decayed. Okay, so then that sort of resets the clock of the decay process and start from the beginning and so forth and so on. So the idea is that by measuring it frequently enough, the atom can never decay because you're constantly collapsing its wave function to the undecayed state. That's Schrodinger's cat. And the question first I want to ask is, do measurements really alter the decay rate of an atom? And the first answer should be no, generally not. And here's the reason why. Think about Fermi's golden rule, which is how you calculate a decay rate. You take the transition matrix element, and you multiply that by the density of states at the appropriate energy difference. Now, the density of states for the electromagnetic vacuum, which dictates this sort of decay, is white. So here's the density of states. The function of frequency is just constant. So generally, the transition, the Fermi's golden rule, doesn't depend on what frequency you choose. It's going to be the same. It really depends on this transition matrix element. Okay. Now, what does the frequent checking on the cat do? Well, what it does is it really broadens this frequency. It is, by opening the box, you're sort of perturbing it, changing its Hamiltonian in some way, shining light on it. So you end up broadening the frequency here, causing it to sample a different density of states, or more or less of the density of states. But since it's constant, you can get the same effective decay rate. So you wouldn't expect measurement or perturbing something like this to change a decay rate as long as the density of states is flat, right? So you might expect this if there was some sort of cutoff, very high frequency. If the density of states rolls off, then you would expect, you measure fast enough, you eventually get to a point where the effective density of states is lower than it is normally, and then you would expect to see some sort of Zeno effect that the decay rate decreases. Okay? But this picture, if I make it kind of more aggressive like this, say the density of states had this shape here, then you could see that you get the Zeno effect. If you measure here, on average, you detect sort of less of density states in the environment, then the decay rate will be decreased, and this is the Zeno effect. But this picture also suggests that there's an opposite effect, that if you go over here, where the curvature is positive, and you measure, now the increasing density of states means that on average you'll have a higher density of states at that transition frequency, or the effective frequency, and this would cause the decay rate to be enhanced. That's what we call the anti-Zeno effect. So Zeno effect, anti-Zeno effect. This seemed like kind of fun idea, so we set up an experiment to try to see these two effects. Fun. Okay, so two ingredients go into the experiment. One is the measurement. We use this dispersive sigma z measurement Hamiltonian that's pretty standard in circuit QED at this point. The way to think of it is the state of the qubit changes the frequency of the cavity. So if I probe the cavity with some coherent tone, I get a qubit state dependent phase shift. If they're well separated like this, I've made a projective measurement onto the eigenstates of the qubit. Second ingredient, we need some sort of peak density of states. So what we're going to do here is take some thermal noise. We're going to filter it to create sort of a very low frequency thermal noise. And then we'll use single sideband modulation techniques to modulate this up to near the qubit frequency. So here's the power spectrum of that bath we create. It has thermal photons. There's maybe 10 of them at the center of the bath, and they fall off. It's like a Lorentzian square. Okay, so we have a thermal noise bath. Now these thermal photons, they induce stimulated emission and absorption in the qubit, and thereby end up shortening the T1 time of the qubit, or the decay time. Okay, so here's the decay, the T1 time of the qubit measured as we change the frequency of the bath relative to the qubit by changing this to tuning. And you can see T1 is like normally 16 microseconds, and then it goes down to like 2 microseconds, and then comes back up to 16 microseconds. It's just mapping out effectively how many photons we have in this bath. Okay, yeah?
So when you drew the picture on the last slide, it looked like you're sampling, whatever your omega 0 is, you're sampling either side of that in this envelope, right?
Yeah.
And so on one side you get the Zeno effect, on the other side you get the anti-Zeno effect. Is that right?
So it's, yeah, so it's when the sampling causes the overall density of states integrated over the bandwidth of the qubit to increase. You have a anti-Zeno effect, and decrease, you have the Zeno effect. I'll show those two on the next slide too. So. Okay, so this is it. So when you have these two pieces, let's put them together. So what I want to do is do a T1 measurement. So we'll put the qubit, okay?
What's the line width of your qubits on this graph?
What's the line width of my qubit? Oh, it's very narrow. The T2 is 10 microseconds or something. And so it's line width, it's very narrow. So it's really just set of like this. It's just sampling exactly the bath. This maps out exactly the shape of that bath via this expression.
So here the x-axis, you tune the qubit frequency around the
So we can tune the frequency of the bath relative to the qubit.
okay, fine. You just move it.
Okay, so now I want to see if measuring, while measuring a T1 measurement, making a T1 measurement changes the T1. Okay, so I'll just create the excited state, and then I'll apply these measurement pulses. They're actually going to be 100 nanosecond long pulses at the cavity frequency. Measure, measure, measure. We put in enough photons so that, in principle, that would separate the two states with unit fidelity. With our quantum efficiency, the fidelity is like 60%, but there's a lot of photons. And so we actually, given the strength of the measurement, it's a complete projective measurement. Okay, so I'll plot the delta T1, the change in T1, which is T1 with measurement minus T1 without measurement, divided by the T1 time, and this is what we see. Okay, so we see Zeno and anti-Zeno effects. So what do I mean? Well, here, where the T1 time, the change in T1 is positive,